Welcome to our presentation on Lewis dot structures. Lewis dot structures are a way of taking a molecule and figuring out what structure it's likely in and how it is bonded to each other and how many bonds it has. And these are extremely valuable when we start to predict what the properties of that molecule are, how it's going to interact with other molecules, and also what shape it's in. Okay, these are all going to be valuable tools that we get out of this. So in celebration of this new principle, we have here one of our favorite dot structures that we can remember back from our kindergarten days. That is the connect the dots. And who knows what this connect the dots possibly could turn out as. But luckily we can count to over 200 and maybe figure it out as we go along. So keep that pleasant picture in mind as we work through this new concept. First of all, the first key to this is we have to do a little bit of review. We're going to be finding the valence shell electrons for atoms. And this is something that I think most of us already understand, so we're not going to take a long time on it. But first of all, let's look at carbon and just figure out how many valence shell electrons it has. Now, the way I like to do this, I find it to be the easiest, is just to find carbon right here, okay, and then count how far it is in the period. Okay, so you count the first atom in that period, which is, lithium here, of course. You go 1, 2, 3, 4. It's 4 atoms into that second period. Therefore, it must have 4 valence shell electrons. All right. Now, that's not just a magical trick or anything like that. The reason that it's the 4th atom in that row is because the second shell holds up to 8 electrons. The first shell only holds 2 electrons. So the first 2 electrons go into the first shell, and the second 4 electrons go into the second shell. Okay, and now you could do this. Alternatively, you could just remember in your mind that 2 electrons go into the first shell and up to 8 go in the second shell. And then you could say, okay, carbon holds 6 electrons. You can say, okay, 2 in the first shell, 4 in the second shell, so there's 4 in the valence shell. Okay, you could do it that way. I like to use the periodic table because it's arranged that way based on electron configuration. That's the reason it has the shape it has. And so it becomes very useful for talking about the valence shell electrons. Let's look at hydrogen. Hydrogen's an easy one. It's right here. Hydrogen only has 1 valence shell electron. Not too hard. Chlorine has 1. Let's see, where is it? 1, 2, 3, 4, 5, 6, 7. Okay, so 7 electrons. And nitrogen over here has 1, 2, 3, 4, 5 electrons. Okay, not too bad. All right, next, something called the octet rule. Now remember that the life goal of every atom, I should say a Y on every there. Let's see, every atom is to have a full valence shell or no shell at all. So for every atom, these over here, these are the atomic heroes. Okay, they are the noble gases. And you'll notice that every one of these has a full valence shell. They all have 8 electrons in their valence shell. And of course, the one exception here is helium, only has 2. And we know why, because the first shell only holds 2 electrons. Now, some of you might be wondering in your mind, why do we have 8 electrons around this kryptonite and xenon? Because if you had learned from electron configuration, you know that those outside shells actually hold more electrons than that. But the reason is, if you remember the way they filled, and a good one to look at was after we get past argon, we fill the outside shell of argon, and we know that the third shell could actually hold more than 8 electrons. In fact, we even see over here the third shell has 18 total electrons. But the key here is that after it puts 8 electrons in its outside shell, the next electron is going to go from, instead of being in the 3p orbital, it's going to jump up to the 4s. So you're going to put your next 2 electrons out here, okay? So a very stable state occurs when you have 8 electrons in that valence shell. Okay, because you don't even fill the next electrons until you actually put 2 electrons in the outer shell anyway. So the point is, and the reason I went through that long explanation there, is that the octet rule can really apply even for those atoms that have more than just 2 shells. They can apply to those with 3 and 4 and 5. And you'll see that as we go along. So the octet rule is pretty handy. All right, and that's what we're explaining there. And then finally, hydrogen we know is one obvious exception to the octet rule, because the first valence shell only holds 2 electrons. And so hydrogen has 1 electron, so it's not going for an octet, it's going for just what they call that a duet. All right, of course we know a duet when we're singing is 2 people singing. In the case of electrons, it's 2 electrons filling the valence shell of a hydrogen atom. All right, so here we go. When we're building Lewis dot structures, we're going to go through a series of rules. And the rules actually, they make a lot of sense as we work with them, and you'll see that you could probably recreate these rules yourself if you needed to. But when you're starting off, the best way to go is to just trust the rules and then know that as you use them, the reason for the rules will make more and more sense. You'll see how it comes together as you build these molecules. So we're going to start off with something quite easy, H2O, and we're going to try to figure out what the Lewis dot structure for H2O is by following these rules. Okay, the first thing we do when we're trying to figure out the Lewis dot structure is we add up the valence electrons for all atoms in the molecule. Okay, in the molecule. So let's take the case of H2O. Okay, now first of all, we have to figure out the valence electrons of H, of hydrogen. Now, we just looked at that, so we're not going to look that up, but we know that it has 1 electron in its valence shell. But we've got to multiply that by 2 hydrogens, since we have 2 of them. Then we go plus, then we look at oxygen. Now, oxygen, we could go back to our previous slide here. Oxygen, oh wait, we got to go all the way back here. Okay, that's too far. Oxygen has 1, 2, 3, 4, 5, 6. Now we go flip all the way through. Here we go. Okay, so oxygen has 6 electrons in its valence shell times by 1 oxygen. So our total electrons in valence shells are 2 times by 1 is 2, 6 times by 1 is 6, total of 8 electrons in the case of H2O. Okay, number 2. Now, let's just make a note here, just in case we have this in a different scenario. We'll show one in just a few minutes here. For each negative charge, we add 1 electron. For each positive charge, we subtract 1 electron. Keep that straight. I know it sounds backwards when you just read it on the surface, but then you think a little bit about it and you say, wait a second, okay, if we have a negative charge, that means we must have had 1 extra electron from what we would have had in the neutral state. If we have a positive charge, that means we must have 1 less electron from what we would have had in the neutral state. So that's why that rule applies. Now, the next thing, this is kind of the part that's more art than science, as they say, because it's not an exact rule, but it's kind of a guessing game, but there's also some good guidelines to help you do this correctly. We want to choose a central atom. Okay? And it says that usually the unique atom or the least electronegative will be the central atom. And then H is never central. Okay? So in the case of H2O, 2 of these guidelines help us out. First of all, the unique atom is oxygen. So we're going to think probably oxygen goes in the middle. And we also see that hydrogen is never the central atom. So that also makes us think that oxygen goes in the middle. Now, technically, hydrogen is less electronegative than oxygen. But these other rules kind of override this one because there's no way to have hydrogens in the middle. And we'll show you why over time. It doesn't work to put them in the middle. They can really only form 1 bond. Okay, so we're going to say the oxygen is the middle. We're just going to assume that we have a hydrogen on the outside here and a hydrogen on the outside here. And again, ignore those little lines. Okay, now number 3, insert pairs of electrons for bonds. Okay, so we're going to put a pair of electrons here and a pair of electrons here. Okay, so that's how we show the bonds. Now, you will see some Lewis dot structures that show the bonds as lines. That's just completely fine to do it that way. But if you see a line as a bond, you have to remember that that line represents 2 electrons. It represents a shared pair of electrons. Okay, now what we need to do is as we add electrons, every time we add a set of electrons, we need to keep track of our accounting because we only have 8 electrons to go around. Now, those of you who have little brothers or sisters might like this metaphor. I just went to my 5-year-old daughter's birthday party, and they had a bunch of cupcakes. You know, and they had a certain number of kids that are at the party, and they had maybe 12 cupcakes, and they had to figure out how to pass those cupcakes out. And it's a trick because you have to pass them out in a way that keeps everybody happy. That's kind of our goal with Lewis dot structures, is we've got, instead of cupcakes, we've got electrons. And instead of trying to make 5-year-olds happy, we're trying to make our atoms happy. Okay, and we've got 3 atoms here that we have to keep happy with 8 electrons, knowing that the goal of every atom is to get a valence shell. So we've got to be creative in how we pass these electrons out so that we keep everybody happy. Okay, so as we go along, one of the keys is we have to make sure we keep track of how many electrons we've committed. Because the worst case scenario would be to say, oh, we'll make you happy later, but now we say we've just run out of electrons. We can't do anything. Okay, so let's keep track of these by, if you look down here, we've used 1, 2, 3, 4 electrons. So we're going to subtract 4 electrons and show that we have 4 electrons left. Okay, so what the next step then, place any remaining electrons around the outside atoms as lone pairs until valence shells fill. Okay, sometimes they call these lone pairs, other times they call them unshared pairs. But what that means is if we have extra electrons, maybe we can fill them around the outside of these outside atoms. But wait a second, we might have a problem. Because look at this part, it says until the valence shells fill. Okay, look at this, what we're talking about here. We're talking about hydrogen. How many electrons does hydrogen fill in its valence shell? I'm sure you know that. It is only 2 electrons, okay? So I just tried to fill 4 extra electrons out here, but wait, we've already got this shared pair of electrons. This shared pair alone fills the valence shell of hydrogen. So there is no reason or possibility of putting extra electrons around the outside of that hydrogen. So we're going to reverse that bad idea we had, because we mistakenly thought that hydrogen could hold more electrons. So now we need to go on to the next rule. The next rule says, if there are more electrons, put them around the central atom. Well, in this case, we still have 4 electrons left to pass out. Okay, so let's give those to this central atom and see what happens here. Okay, now let's see what happens. Remember, our goal is to give everybody a valence shell while only using the electrons or cupcakes we have available. And have we accomplished that? Let's see here. With this hydrogen, does it have a full valence shell? Yes, it's got 1, 2 electrons in that shared pair that make up the bond. So that is a full valence shell. This hydrogen, it also has a full valence shell. Now let's look at oxygen. 1, 2, 3, 4, 5, 6, 7, 8. It has 8. So we have succeeded. This is the Lewis dot structure for H2O or water. Now, just in case we get to the step, and we will on the next slide, if the central atom is not filled, use lone pairs from the outside atoms to form double or triple bonds. Okay, so this is something that we do if we have not already filled the valence shell of the central atom. So we're going to practice a few of these. Now, these will get more complex on the next slide, so get geared up. And we're going to learn how to work through this. We'll be flipping back and forth to see these rules. Okay, first of all, a little more challenging. We're going to try CO2. Okay, we have to figure out what the central atom is. Now remember, the unique atom, actually, before we figure out the central atom, let's first add up the valence shell electrons. Okay, so the carbon has 4 valence shell electrons. Okay, now I'm going to show you this because we can look on this chart here, and we can see right here, carbon has 1, 2, 3, 4. Okay, good. You guys know that. Okay, so we're going to put 4 electrons times by 1. And then plus, oxygen has, okay, where's our oxygen? Is right here. 1, 2, 3, 4, 5, 6. 6 electrons. And we're going to multiply that by 2 times by 2. And our total electrons is going to be 4 plus 12 is 16 electrons. That's our total electrons, our total cupcakes that we have to pass out. And the question is, how are we going to pass these out? So the next step is figure out our central atom. Now, we said it's usually the unique atom, okay? And it's also normally the least electronegative. Both of these rules hold true in this case, okay? We have one unique atom, that's carbon. It also happens to be more electronegative than oxygen is, okay, because carbon's right here and oxygen is over here. And so we know that the trend of electronegativity, as you remember from the last test, goes this direction. And so oxygen is more electronegative than carbon. Therefore, carbon is the least electronegative. Therefore, it is the central atom. So let's take that over here. Let's put a carbon. I'm going to put an oxygen here, and oxygen here, and an oxygen here. Okay. Now, the next question is, what do we do with our 16 electrons? How do we pass those out? Well, the first thing we do, I'm not going to look back on this one because it's going to be something you're going to get to where you remember, but the first thing we do is we put an electron pair for each of the bonds. 1, 2, 1, 2. Now remember, a shared electron pair represents a bond. We could also have a straight line to represent that bond. That's what that means. Okay, now the next step is we need to figure out what we do with, now let's actually put here, let's keep track of our electrons. We just used up 4 electrons, making 12 electrons left. It looks like one of our electrons disappeared. So now we have 12 electrons left. We used up 4 through bonds, and the 12 electrons, remember the next rule is place any remaining electrons around the outside atoms as lone pairs until the valence shells fill. Okay, so let's do lone pairs out here. This can hold 1, 2, 3, 4, 5, 6 more. Now that oxygen has 8 electrons around it. It is following the octet rule. It doesn't hold any more. Okay, we never go past 8. 1, 2, 3, 4, 5, 6. Okay, so we just added, let's keep track of our electrons. We just added 6 on this oxygen, 6 on this oxygen. That means that we have 12 electrons that we have just added, leaving us with the big goose egg left. I hope everyone's happy, but guess what? I don't think they are. We need to figure out a way to rearrange our electrons or redistribute our cupcakes to keep everybody happy. Okay, so let's see what we can do. Let's go to the next rule. It says if there are more electrons, put them around the central atom. Well, sorry, we're out of electrons, so we can't give any more to the central atom. But let's look at number 6 here. If the central atom is not filled, use lone pairs from outside atoms to form double or triple bonds. Ooh, okay. So our central atom only has 4 electrons around it, and we want to have 8 electrons around it. And so it says to use lone pairs from outside atoms to form double bonds. I'm going to take this lone pair, I'm going to put it down here. I'm going to take this lone pair, I'm going to put it down here. And then we are going to end up, I'm going to redraw this because it's looking a little bit sloppy now. I'm going to redraw this. I'm going to put a carbon, and it's got, okay, just a second here, try this again. It's got 1, 2, 3, 4, and then the oxygen. And then on this side, 1, 2, 3, 4, and then the oxygen. And then it's got still 1, 2, 3, 4, and 1, 2, 3, 4 around the outside of the oxygen. Okay, now that looks a little bit sloppy, but that is essentially the Lewis dot structure for carbon dioxide. Sometimes when I finish these, I like to draw it with actual lines for bonds because it tends to look a little bit clearer sometimes. But anyway, here is essentially what you've got with 1, 2, 3, 4 electrons around that one, and 1, 2, 3, 4 electrons around that one. So this and this, these two mean the same thing, okay? But that is essentially because each of these bonds is 2 electrons. So you're showing here 4 electrons. Okay, the next one's a little bit trickier. I'm not going to take too much time on this one because it's a little bit different, but I'm just going to talk through the rules without flipping back and forth. So you'll kind of want to maybe, I'll have a worksheet that has the rules on it that you can follow along with, but I don't want to focus too long on this one. only because it's a little bit unusual, but I want you at least to see how you would deal with this. Now, this is unusual because it doesn't have one unique atom. You kind of have two central atoms, okay? Whenever you have carbon, carbon is usually the central atom, and that is the case here because we also know that hydrogen is never the central atom. So we're sort of zeroing in there on carbon. So we're going to put two carbons, one carbon here. So one carbon here, and then we're going to put two hydrogens out here on the outside around those carbons. One hydrogen here, one hydrogen here. So this is partially a guess, okay? But there's not too many other configurations you can come up with. And you're going to find really quickly that hydrogen can only make one bond. And so there's not too many other ways you could put this together in this case. There will be other atoms, there will be other, molecules that are tricky to predict, but we'll try not to have those on any sort of test. We're going to have ones that have a pretty clear prediction that you can work with. So the first thing is we arrange it the way it most likely is formed. Then we use up 2 electrons for each of the bonds. And we forgot to do one thing, and that was, sorry about the little lines, we're going to ignore those. We just used up 2 electrons for each of the bonds, but we forgot to, at the start, do our accounting. And let's do that really quickly to catch up. We have carbon has 4 electrons in its valence shell, times by 2, plus hydrogen has 1 electron in its valence shell, times by 4, leaving us with, let's see, 12 electrons in our 12 valence electrons in our entire molecule. All right, and we've already used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've already used up 10 electrons for the bonds. Okay, leaving us with 2 electrons left. Okay, what do we do with those? Okay, now the first thing we want to look at is if we can fill any more electrons in these valence shells of the outside atoms. And the answer is no, we cannot put any more in those because they are already filled. Okay, each of these have 2 electrons, and hydrogens can only hold 2 electrons. So then the next thing we do is we say, okay, can we put any more electrons in our central atoms? Okay, so let's look at this. This carbon has 1, 2, 3, 4, 5, 6 around it. This carbon has 1, 2, 3, 4, 5, 6 around it. Okay, so how many electrons can carbon hold in its valence shell? That's right, it can hold 8. It follows the octet rule. And so we've only got 2 electrons to go, and we've got 2 carbons. So how can we get it so that both of these get to a full valence shell? Okay, well, one thing we could do is, well, let's just do it the right way, because we could say, first of all, we could say, okay, we could put these 2 electrons on one of the carbons. That would fill the valence shell for that carbon, but it would leave this carbon only with 6. So this goes to the last rule. The last rule says if we haven't filled the valence shells of the inside atoms, then what you need to do is you need to take 2 electrons from one of the outside atoms and turn them into a double bond in the middle. Okay, and so we're going to do a quick eraser here. So what we're going to do is take these 2 electrons here, and we are going to stick them in the middle here, and we are going to form a carbon bonded to a carbon with a double bond, and then the hydrogens are around the outside. That is our result, because if you go around, you'll notice that every one of our atoms has a full valence shell. Okay, and again, sometimes I like to redraw these at the end, and this would look like, just so you know how this looks, carbon to carbon to hydrogen to hydrogen. Okay, this is called ethene, is the name of that molecule. If you are when we get into the biochemistry unit, that's what you would call that, or the organic chemistry unit. All right, next part here is nitrogen trichloride. How does this one work? Let's do our accounting really quickly. Nitrogen has, I'm just going to work through this quickly, so we'll erase that. So we've got 5 electrons in our valence shell of nitrogen, times by 1, plus 7 electrons in the valence shell for chlorine times by 3, and that's going to equal 5 times by 1 plus 7 times by 3 is going to be 20. So we got 21 plus 5 is 26 electrons to deal with. Okay, now we're going to kind of move over here so that we just have room to work with. All right, so now we then try to figure out what our central atom is. In this case, we go to that rule that says usually the unique atom or the least electronegative. Okay, well, in this case, is nitrogen more electronegative than chlorine? Well, those are hard to compare because nitrogen is in the first row, but chlorine is more to the right. I believe that chlorine is a little bit more electronegative, but regardless, we also know that nitrogen is the most unique. And so we're going to put the nitrogen in the middle. All right, let's put nitrogen here, let's put a chlorine here, and a chlorine here. All right, now we need to make the two extra pairs of electrons for our bonds. Okay, so now we just used up 6 electrons. So just to keep track of our counting, 6 electrons, we're left with 20 electrons we still have to account for, 20 cupcakes to pass out. See if we can make everybody at this little party happy. And so the next thing we do as we look at our rules is we place any remaining electrons around outside atoms as lone pairs until valence shells fill. All right, so I think we can do that. We've got 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we just have used up 18 electrons to fill the valence shells of each of these chlorine atoms. Now, each of these chlorine atoms has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons around it. So now we have to say subtract 18 electrons, and that's going to leave us with 2 electrons left. What are we going to do with those 2 electrons? Let's see here. If there are more electrons, put them around the central atom. Okay, so in this case, does the central atom need more electrons? It's got 1, 2, 3, 4, 5, 6. So nitrogen can hold, it follows the octet rule, it can hold up to 8 electrons. So yes, we can put 2 more electrons around that. And there we go. This is the Lewis dot structure for nitrogen trichloride. And you could also turn that into these like this if you want. This means the exact same thing with our lone pair here. That means the exact same thing, essentially. All right, now this last one's a little bit more challenging. That throws a little bit of a curveball at us. So let's try it really quickly here. Nitrogen has 5 electrons. Let's add up our, so we got 5 electrons times by 1, plus oxygen has 6 valence electrons times by 3. And we're going to get a total of 5. So we've got 18 here plus 5. So we have a total of 23 electrons. Okay, but notice this. It has a -1 charge. So we have to add to that 1 electron. Okay, so the total we have to work with is 24 electrons. We've got 24 electrons or cupcakes to pass out. And see if we can make this little party of 4 happy with 24 electrons. Okay, now next, we have to decide what is the central atom. Now in this case, oxygen is actually more electronegative than nitrogen, but nitrogen is the unique atom. Okay, and so in this case, you would put nitrogen as the central atom. Okay, so when you have a unique atom, it's almost always, or when you have a unique atom, it's almost always going to be the central atom. Okay, so in this case, I know we're getting a little bit tight down here, but we're going to put nitrogen as our central atom. We're going to put an oxygen right here, an oxygen right here, and an oxygen right here. Okay. Now, what we're going to do is start putting our little electrons in the middle here. See if we can get them all in there. We just used up 6 electrons. Let's keep track of our accounting. -6 electrons, leaving us with 18 electrons. Next, we're going to, if we look at the next rule, I'm not looking at it, but I'm trying to keep it memorized now. The next rule is to fill the outside electrons until their valence shells are filled. So we're going to put 1, 2, 1, 2. So we're putting that. Now that oxygen now has a filled valence shell. And then this oxygen now has a full valence shell. And this oxygen now has a full valence shell. All right, how many atoms have we used up? We just put 6, 6, 6, 6, 6, 6. So we've got 18. We just used up 18 electrons, leaving us with 0. We've got nothing else. Have we made everybody happy? And this one's happy. This one's happy. It's got 8 electrons. This one's happy. It's got 8 electrons. Are we done? Wait. Uh-oh, our middle atom here only has 6 electrons around it. That atom is not happy. Okay, so we've got to go to our last rule then. If the central atom is not filled, use lone pairs from outside atoms to form double or triple bonds. All right, so what we need to do here is we need to take 2 electrons from an outside atom like this, and we need to have them come down to form a double bond. Okay, so now I'm going to redraw this twice. So first of all, this is what we now look like. Oxygen, we've got 2 here. So 1, 2. And this one is going to have 1, 2, 3, 4, and then 1, 2, 3, 4. Okay, so now we've formed a double bond here between the nitrogen and one of the oxygens, and then we have single bonds between these ones. So in other words, here's kind of what it looks like. I'm going to leave out the so single bond, like that. Okay, and that's how. And then here's the important thing, is that because we've got a negative charge, here's one thing that I didn't mention in the rules, is that once you have the overall atom, you should put brackets around it and put a negative charge to show that this atom has an overall, or this molecule has an overall negative charge. And that's all based on the fact that if you count up all of your electrons, you know that you've got 1 extra electron than you have total protons. And actually, you don't even have to know that. You just know that from the start, you're supposed to have a -1 charge. And so you put that on there. There's one other curveball with this one, and it's something that we call resonance structures. Let me just tell you this, just so you know what's coming up. But what actually happens here is this double bond, we chose this oxygen, but we could have just as easily chosen this oxygen right here to form a double bond, or we could just as easily have chosen this oxygen here. Okay, so all of those would have been an equally satisfactory option for forming a double bond. So what actually happens in the case of nitrate is that bond is actually shared between all 3 of these bonds between the nitrogen and oxygen. So it's kind of like that double bond sort of like shifts around. It's like, say it's like between this nitrogen and oxygen for a split second, then it goes between this nitrogen and oxygen for a split second, then it goes between this nitrogen and oxygen for a split second. And it kind of moves around a bit between all 3 options. Okay, that's something that we call resonance structures. It's not something we're going to cover in depth right now, but it's something I want you to keep in mind as we get into the next section. So hopefully that was useful to you as we went through and we explained Lewis dot structures. I've got to admit, this page looks like a complete mess right now. So hopefully as we worked through it, you followed the way through it. But the good thing is we will have a good worksheet that's going to help you to make sure that you understand this. And I can tell you that Lewis dot structures are easiest to get down by practicing them. There is one more thing that I've seen come up. I didn't ever actually use this when I learned chemistry originally, but I've seen it in high school curriculums a little bit. You see there's something called the HUNK 1, 2, 3 rule. And what that refers to is if you go hydrogen, oxygen, nitrogen, and carbon, then they form in order 1 bond, 2 bonds, 3 bonds, and 4 bonds. Okay, and this is kind of helpful to know that carbon normally forms 4 bonds, nitrogen normally forms 3. So let's just put the numbers above it. 4, 3, 2, and 1. You can see this when you look over here at their actual Lewis dot structure, because you remember, if we just imagine carbon binding to hydrogens, if the carbon contributes 1 electron, the hydrogen contributes 1 electron, then we get essentially 1 bond there, 1 bond there, 1 bond here, and 1 bond here. That makes 4 bonds. And you can see that that's how that valence shell gets filled, because when each of the bonds that it forms essentially adds 1 extra electron to that valence shell, it's got 4 electrons to make up for, so it's going to make 4 bonds. Same thing here. If you imagine hydrogens going along the outside there, you're going to put 1 there, 1 there, 1 there. Again, it's got to fill 3 extra electrons here to fill its valence shell, and so it can make 3 bonds. Same principle with oxygen, and look at that. There we go. There's our water. And then with hydrogen, same idea, where you'd put 1 hydrogen, and this is hydrogen gas, H2, H2O here, NH3 here, something called ammonia, and CH4 here, something called methane. So that's a common, just a good way to remember that carbons make 4 bonds, nitrogens make 3 bonds, oxygens make 2 bonds, and hydrogens make 1 bond. Just a little helpful hint for you. And that'll do it for our video today. Hope you have a great day. We will catch you next time.